Good afternoon, everyone. I appreciate you joining us for this webinar. The topic is the safety life cycle. It's an overview of the safety instrumented engineering life cycle that is documented in ISA's 84 standard. We'll be providing you with a brief overview of all the major steps of the life cycle, giving you some insight into the importance of each of the steps in the life cycle and some practical insight in terms of implementation of those steps. Although the content of the webinar is essentially non-commercial, we will just provide a little bit of information about Kenexis Consulting Corporation. We have about 20 engineers on staff, and our capabilities are in hazard risk analysis, control systems engineering, and chemical process engineering. We really provide the best and brightest of talent in terms of integrating those three elements to provide value in terms of robust design and implementation of safety critical control systems, which include safety instrumented systems. You've heard a little bit about me. Just to add to that, my background in safety instrumented systems engineering is approximately 10 years now that I've been involved in this practice area, and I've been doing this in various industries, including upstream oil and gas exploration and production, downstream petroleum refining and marketing, and a variety of petrochemicals and specialty chemicals applications. So to get into the content of the safety life cycle, we need to ask the question, why do I need a safety instrumented system? Processes contain toxic and hazardous materials, including flammable materials, processing equipment that's at extreme temperatures and pressures, and most companies use a variety of means to control risks and bring them to a tolerable level, including administrative controls as well as engineered safeguards. Administrative controls would be procedures, design practices. Engineered safeguards are equipment including safety instrumented systems as well as other types of equipment such as pressure relief devices, fire and gas systems, secondary containment systems that, when in combination with administrative controls, these engineering controls allow the plant to operate at a tolerable level of risk. Common safety instrumented system applications. There are a variety of applications out there. It does depend a little bit on the types of industries that are involved. They can be found in a variety of industries. Here are some typical applications, including emergency shutdown systems. We see a lot of safety instrumented systems on fired equipment, including burn management systems, on flame safety systems, as well as systems that are designed to specifically operate at a high level of integrity and protect systems against overpressure. We call those high integrity pressure protection systems, as well as a variety of other systems out there in process plants. Really, to obtain a good understanding of what a safety instrumented system is, we have to work within some standard definitions. The ISA standard does provide definitions of safety instrumented systems. A more practical alternative is a system that detects out of control process conditions and, importantly, automatically returns the process to a safe state. It can do those actions without intervention of an operator. It is the last line of defense or near last line of defense. It is outside what we would define the day-to-day or basic process control system within a plant. So it's a system that takes usually fairly extraordinary actions to shut down a process, or in the language here, return the process to a safe state when certain predefined safe operating limits have been violated. Those are the out of control conditions that would prompt a system like this to shut the process down. That's a common practical definition of a safety instrumented system. They differ from the basic process control system in two important ways. One, they're functionally different from the basic process control system, as I alluded to, that the BPCS, or basic process control system, handles day-to-day, routine, ordinary control actions. A safety instrumented system would handle non-routine, extraordinary actions which shut down the process when certain predefined limits have been violated. They're usually physically separate systems, although it doesn't always need to be that way, and of course there are certain drivers within the industry now to combine certain elements of the basic process control and safety instrumented systems. But in the traditional engineering sense, those systems not only are functionally separate, but they are physically separate. They do not share components, including control system components as well as field devices like process sensors and final control elements. So they're physically and functionally separate systems. A safety instrumented system is comprised of various components, including sensors, logic solvers, and final control elements. These are the three subsystems that make up a safety instrumented system. There could be single loop control systems that qualify as a safety instrumented system, but more commonly we see a variety of process sensors and final control elements that have been integrated into a single system using typically just one safety logic solver, and that is the boundaries of the safety instrumented system. As I mentioned, it's comprised of different components, including field devices that are separate from the basic process control system. The sensors are separate. The final control elements are separate. And typically in the middle we have a safety instrumented system logic solver, which could be a programmable device but doesn't always need to be a programmable system. It could be a electromechanical system. It could be a pneumatic and hydraulic based system, as we often find in upstream oil and gas on minimally attended installations. But typically, this is the boundaries of the safety instrumented system, including the logic solver and the field devices. During the development of the ISA standard, importantly, it was recognized that not only that logic solver, but also the sensors and the final control elements could play a critical role in ensuring the overall functional safety of a plant. And at that point in time, the standard was somewhat broadened to include elements such as safety transmitters and safety final control elements, including shutoff valves or motor starter equipment that could play an important role in achieving functional safety. It was recognized by the standards making group and the committee that a failure of any of these components could result in a situation where a safety function was inhibited from performing its intended action on a demand, and therefore the standard takes a fairly holistic approach in looking at the overall safety loop and determining the likelihood of success, the likelihood of failure, and ensuring that the system is designed robustly enough, as I mentioned earlier, to meet a tolerable risk target. There are certain legal requirements for safety instrumented systems that vary from locality to locality. For the purposes of this presentation, we'll limit the discussion to U.S. legal requirements for safety instrumented system, and I have to point out these are not all the legal requirements that might apply between certain localities in the U.S., but it is true that generally the regulations that govern process safety in the United States are based on recognized and generally accepted good engineering practices. And the role of the ISA and more broadly the IEC, the International Electrotechnical Commission, has been to clarify the regulatory requirements for safety instrumented systems by offering the ISA's S84 standard, which has now been harmonized with the IEC's 61511 standard, and to offer that as the means to describe what is a good engineering practice, one that's recognized throughout the industry, and furthermore, one that has been generally accepted by many operating companies within the industry. OSHA has recognized ISA 84 and provided an endorsement saying it is one way under the Process Safety Management Standard OSHA PSM 1910-119 is one way to meet the requirements in that standard for mechanical integrity, testing of safety critical devices, as well as process safety information or the design documentation of good engineering practices for safety critical devices. Why the new SIS standard? There's a significant amount of history as to how the standard was conceived, how it has evolved during the initial formulation of the standard and publication back in 1996, and how it has evolved since that initial publication into the revised standard that was issued in 2004 by the ISA. When we look out across industry and see a number of different accidents that have occurred and incidents that have implications in the area of safety instrumented system design, they fall under these general categories that range from accidents occurring because, or at least in part because, no safety instrumented system was installed, to poor design of those systems, poor testing of those systems to ensure they are properly functioning at all times, as well as a number of incidents that occur because of improper bypassing of equipment. So to understand the safety life cycle, I believe it's important just to highlight a few of these incidents, and we'll do that before we get into essentially a roll call of all the elements of the safety life cycle. In 1999, an incident occurred in Allentown, Pennsylvania, involving the initial startup of a distillation system that was producing purified hydroxylamine, or HA in this case. The system was almost exclusively operated by manual means of control. There were no systems in place that automatically detect an out-of-control process condition and shut the process down. And in this case, the incident occurred because of an overconcentration of this highly reactive chemical, a concentration beyond the safe operating limits. And the result was a detonation that resulted in several fatalities, including one fatality involving a member of the public. And now, there are a number of causal factors associated with this, as well as all major incidents, but I would at least posit the thought that for a scenario where there could be such severe consequences that a system that automatically detects out-of-control process conditions and shuts the process down automatically might be considered as a valuable component in the overall risk management structure if certain hazards and risks like this are involved. In this case, there was no SIS available. Another case occurred in 1998 in the refining industry in Martinez, California, when a process involving a hydrocracker involved a runaway reaction. In this case, there were many sensors in the process that were able to detect an out-of-control process condition, but there was no system that was automatically configured to shut the process down. And in fact, in this case, it was exclusively relied upon for manual action to occur to shut the process down. And during the day of the incident, there were indications that an out-of-control runaway reaction was occurring, but prompt action was not taken in a timely manner, and the result was, unfortunately, a fatal incident that involved a pipe failure in the outlet of a runaway reaction in the outlet of a reactor because of this particular high-temperature thermal excursion. We see a number of incidents that involve improper testing methods. In 2002, an incident occurred in Missouri involving a chlorine release in which a hose rupture occurred when offloading chlorine from a tank car to a fixed facility tank. There was a safety instrumented system that was designed specifically to detect an out-of-control condition like a line rupture and to shut the process down. That system did activate in this case. However, the valves did not properly seat and prevent the chlorine release on either side of the ruptured hose. Those valves had been tested and very frequently tested, but in improper manner that failed to prove that they are actually capable of preventing flow through a ruptured hose in this case. In 1994, we saw an incident that involved a runaway reaction in a batch chemical reactor. In this case, there were relatively poor selection of the components in the system and a system that allowed an operator to reset the system multiple times when given information about an already gross mischarging of material in the reactor. In this case, the reaction was allowed to continue. It initiated a violent exothermic runaway well beyond the capability of the vent system, and in part because of the poor selection of equipment within the safety instrumented system and the poor basis of the overall design, several life-threatening injuries occurred in that particular incident. There are certain implications of the accident data that we draw from these variety of incidents that I've showed you, as well as others. They are important to determining the overall structure of the safety life cycle. As you can see, some of them involve the criteria of when to use alarms and operator judgment versus an automatic shutdown philosophy. Others involved not applying a defense in depth strategy where we don't put all our safeguards, our eggs in this case, into one basket, that we separate those protection layers such that even if one layer fails, there will be other layers we can rely on to have the opportunity to protect the process from an out-of-control process condition. We see a lot of these accidents that involved improper design specifications for safety instrumented system components, or the overall architecture is not provided with what we call a fault-tolerant architecture, that there's improper testing and diagnostics of components in those designs to ensure that they work and are robustly tested on a regular basis. And I have to say, with great regret, not only in the past but even recently, we continue to see incidents that involve operator bypass and defeat of safety critical systems. Too often we see safety systems that are well designed, well intentioned, but are all too easily bypassed and are done so in an effort to maintain control of the process by an operator in the face of already out of control process conditions. So those are some of the implications of the accident data and what it might mean to proper design of a safety instrumented system. The ANSI ISA standard for the S84 provides a safety life cycle that is intended, I think in broad measure, it's intended to address most, if not all, of these root causes or underlying causes of failures that we see in the accident data. The safety life cycle is intended to identify and provide a proper basis for the design of the systems, to provide a robust design in terms of component selection, overall architecture. It provides for robust diagnostics and testing, as well as management of change and ongoing maintenance of those systems. The safety lifecycle approach was included in the original S84 standard that was promulgated back in 1996 and has been broadly updated and added upon using the International Electrotechnical Commission, or IEC's 61511 standard that has been harmonized with S84 and promulgated in the latest 2004 version of the standard. So what does ANSI ISA 84 require? It's a performance-based standard that doesn't prescribe every design decision in a safety instrumented system, but it does outline a broad safety life cycle and allows companies to tailor-make their own programs within that safety life cycle that achieve the overall performance goals of a functional safety plant, or a plant that ensures that out-of-control process conditions do not occur through a use of safety instrumented system. It does require, and this is the difficult part for a lot of operating companies, it does require each safety system, in fact, even each function in those safety systems, to select a performance target, and then requires that those performance targets be confirmed, that achievement has been quantitatively verified that we have achieved those performance targets. That's in a nutshell how I describe the safety life cycle. If somebody asks me, puts me on the spot and says, what does it require? It requires you to choose a target and prove that you've met that target. That's a performance-based standard that S84 is. The safety life cycle that I'll put up on the screen here is the safety life cycle in the 2004 version of the standard, and there are a number of elements to it. It's really, as I mentioned, a life cycle. What does that mean? It's sort of a cradle-to-grave approach to achieving functional safety in a plant. And the cradle is really at the beginning, where we're evaluating hazards and assessing those risks all the way through the decommissioning of a process. Along the way, we need to allocate protection layers or safety functions, which is really the heart of selecting a safety integrity level for your safety functions. It's picking your SILs. Providing a safety requirement specification that can be used during detailed engineering and design that ensures we've met the requirements of the standard and in a way that will achieve the SIL that we've selected for each of those safety functions. Going on through the various clauses that involve installation, commissioning, and validation, that's sort of the end of the design phase and implementation phase of the safety instrumented system, and then it's turned over to the operation and maintenance phase. Along the way, of course, we can have modifications that need to be properly managed, and at the end of the life cycle, we might have to decommission part or all of the safety instrumented system without impacting other systems around it. And in the current version of the standard, we have various elements that cut across all of the different steps or tasks in the safety life cycle that involved planning, functional safety assessments, and auditing to make sure that we've done the tasks that we've set before ourselves. And this element of verification to ensure that the outputs of each step in the safety life cycle have been satisfied in a manner that's consistent with the inputs. That's the safety life cycle that you will see if you open up a version of the standard. We've taken the liberty of recasting it a bit in a typical design project where we're designing new equipment in a process plant. It fits better if we describe it more in this fashion, where we're going through each of the steps from analyzing the hazards, defining safety functions or SIFs in the system, going through a process of selecting SILs for each of those systems, or safety integrity levels, then going through a conceptual design step and verifying that we've achieved the SIL targets in that conceptual design. We then develop design specifications, which would be equivalent to the safety requirements specifications required by the standards, and go through the various other tasks that would be typical of any instrumentation and automation project, but have specific requirements because we're involved in a safety system. So let's go through and unpack briefly each of those elements, and that will constitute the overview of the safety life cycle that we're intending to achieve with this presentation material. The first step is really a conceptual process design. It's the starting point where design is selected. It's not part of the safety instrumented system, but it's really the starting point for all the other activities that go on in the process. Conducting a process hazards analysis is the first major step. Of course, many companies have been doing this and had been doing process hazards analysis well before ISA got involved, but the important factor here is that to design a safety system using a performance-based standard, we need to know the basis of that design. What hazards are we intending to protect against with that system? What are the severity of those hazards? How likely could they occur? And that is the type of information now that we need to have in our process hazards analysis reports, because it's being drawn on as the basis of the safety system design. There are, of course, multiple ways to conduct process hazards analysis. Usually this is a facilitated meeting, but we try not to think so rigidly about it. There are many ways in which we can identify process hazards, from reactivity studies. Process licensors provide us valuable information about the types of hazards, and design standards and practices that have codified things for typical systems, especially systems like fired equipment, which tend to use the very same safety functions again and again. They provide us valuable information about what the potential hazards could be from certain out-of-control process conditions. Coming out of the PHA, or Process Hazards Analysis task, we move into a SIF definition, where we're defining safety instrumented functions that will eventually be implemented in a safety instrumented system, and we create a list of those safety instrumented functions. Of course, we have tools that we can use to accomplish this. We use certain information from the PHA report, as well as P&IDs and cause and effect diagrams as the basis for developing that list of safety instrumented functions. And we provide it in a format where we define those safety functions based on all the hazards that are intended to be protected by the system. We provide a definition that includes all the ways to detect those out-of-control process conditions or hazards. Those would be the inputs to the safety functions, as well as the actions, or those things that we can use to shut the process down and move it to a safe state in the presence of those out-of-control process conditions. And we do this on a hazard-by-hazard basis to make sure that all the hazards that we're intending to protect against are part of at least one safety instrumented function on the list. Once we have a list of safety instrumented functions to evaluate, then it's important to then move to the next step where we are selecting the appropriate safety integrity level targets for those safety functions. The standard really doesn't say how to go about doing this. It offers a few suggestions of different methods that can be used, and commonly in industry now, most companies are using a method called Layer of Protection Analysis, or LOPA, as the means to accomplish SIL selection. But it's important to understand that the goal is to select the SIL rather than to conduct a LOPA. So what we are trying to convey here is that for every safety function on that SIF list, we have gone through and selected an appropriate safety integrity level target for those safety functions based on some analysis protocol which looks at the hazard, the potential severity of the hazard, the likelihood of the hazard, and determines the amount of risk reduction that that safety function is required to achieve. And we categorize that amount of risk reduction as either SIL 1, SIL 2, SIL 3, or possibly even SIL 4, which are orders of magnitude of effectiveness, essentially, of a particular safety instrumented function. A SIL 1 provides at least one order of magnitude of risk reduction. SIL 2 is an order of magnitude better than a SIL 1 and provides at least 2 orders of magnitude of risk reduction, and SIL 3 and SIL 4 are so on. So a SIL 1 provides at least a risk reduction factor of 10, will fail, or rather has a safety availability of at least 90%, and conversely has a probability of failure on demand of less than 10%. A SIL 2 has a safety availability of at least 99%, up to 99.9%, will fail no more than 1% of the time and provides a risk reduction factor of at least 100. SIL 3 provides at least a safety availability of 99.9% and a risk reduction factor of at least 1,000. So the objective of SIL selection is to determine the level of risk that will require a SIL 1, specify a SIL 1 where it is needed. If we have a higher level of risk, higher hazard, then perhaps a SIL 2 or maybe even a SIL 3 is required to achieve a level of risk that's deemed tolerable. Importantly, no SIL on this list, even a SIL 4, reduces the probability of failure to 0 or provides 100% safety availability. In this type of performance specification, we need to understand what level of failure we can tolerate. In certain circumstances, we may be able to tolerate only a very small possibility of failure. That's a situation where we have a very high level of hazard and perhaps very few other protection layers available other than the safety instrumented system. In other systems, we may have more margin, we may have other protection layers, and we may require less of our safety system. In those cases, perhaps a SIL 2 or as low as a SIL 1 may be required. Those are the definitions of safety integrity level, and the process of specifying the correct safety integrity level varies from company by company. There's no mandate in the standard to use a specific level of risk tolerance or even a specific method for selecting SILs, but most operating companies currently use a process where the level of risk is evaluated for the process using both consequence and likelihood, and we start with the inherent risk of the process, which is a product of that consequence and likelihood. We reduce that risk using all non-safety instrumented system layers protection, things that could reduce the consequence, things that could reduce the likelihood, such as relief valves, operators responding to alarm, and then we assess the risk in terms of where we're at with respect to some risk tolerance decision making. That here in this graph is only presented in concept, but in reality, for each company that applies the standard would have some quantitative or qualitative means to draw the lines of what's a tolerable level of risk, what's an unacceptable level of risk, and what's a level of risk in the middle that might require further risk reduction if the cost-benefit equation is favorable. After we've taken credit for and considered all the non-safety instrumented system level of risk reduction, then we look at the SIS risk reduction that's required to achieve a tolerable level of risk and assign the appropriate level of SIL to that safety instrumented function, whether it's a SIL 3, a SIL 2, or in this case, conceptually, as low as a SIL 1 might be required to get to a tolerable level of risk. In some cases, of course, the level of risk would be deemed already tolerable without the benefit of any safety instrumented function, or on the more extreme end, even a SIL 3 or a SIL 4 system may not be able by itself to achieve a tolerable level of risk, and those risk decisions would have to be confronted on a case-by-case basis. As I mentioned, in practice, the decisions are usually made using some qualitative or quantitative metrics, in this case just displaying a risk matrix as one means to determine where a SIL 1 might be required, where a SIL 2 might be required, and where a SIL 3 might be required. The method for determining the proper SIL is based on a layer protection analysis where the preventative as well as mitigative hazards or safeguards are evaluated and assessed whether the safety instrumented system by itself can mitigate the level of risk to a tolerable level, whether process alarms with operator response are required, whether physical devices like relief valves are required to protect in combination with the safety system to achieve that tolerable level of risk. So most companies are using this method of considering all the preventative layers of protection and assessing credit for each of those different layers before deciding whether a SIL 1, 2, or 3 shutdown is needed. We can move after we've selected the SIL required for each of the safety functions. We can move from the SIL selection step to the conceptual design and SIL verification steps, which really are an iterative loop where we start with a conceptual design, we run it through the SIL verification process, and we may have to iterate a few times to get to a design that meets the SIL targets as determined by SIL verification. In conceptual design, we're making design choices that might impact our ability to meet the SIL target, including selecting the equipment that is appropriate for the SIL that has been selected, specifying an architecture, in some cases a fault-tolerant architecture, to achieve that SIL target, and specifying functional testing that allows us to achieve that SIL target. In the end, we produce a safety requirement specification to define what that design is, and I'll go into that a little bit more in the next step. In component selection, certain components are certified for use in higher SIL applications, and we may have to select those components in order to achieve that SIL depending on the SILs that have been selected. We may have to choose a fault-tolerant architecture. We may have to define functional testing intervals that are more frequent than turnaround testing to achieve our SIL targets. And we may have to produce a design that provide some diagnostic testing of the design of the components on an ongoing basis to make sure that there are no faults present. Component selection, as I mentioned, there are some components that are certified for higher SIL levels. They're typically done so by the manufacturer, and a certificate would be provided by the manufacturer describing how the design for meeting, say, a SIL 2 or a SIL 3 target is in accordance with the 61508 standard, or we may be able to do a proven in use assessment of existing components in the process to achieve a demonstration that the component is suitable for use in a particular SIL application. Part of the decision-making process, regardless if we're going to use a certified device or using a proven in use assessment of an existing device, would be looking at parameters such as the safe failure fraction of those devices. And of course, in the current offerings that many of the equipment vendors have, they have transmitters that are certified for use in single devices, in some cases up to SIL 2 or even SIL 3 applications. Fault tolerance is the concept of using multiple devices in an architecture that decreases the overall probability of failure. The typical voting architecture that reduces the probability of failure is a 1 out of 2 voting architecture, where either device has the ability to put the process into a trip state regardless of the function of the second device. That reduces the probability of a dangerous failure, but increases the probability of a safe failure or a spurious failure of the process. The combination of voting architecture that provides both a low probability of failure and a low spurious trip rate would be, say, a 2 out of 3 voting architecture, where 3 devices are used, requiring 2 out of any of those 3 devices to vote to trip in order to take the specified safety action. Of course, higher levels or required SIL levels will typically require some degree of fault tolerance, both in the field devices, those transmitters and valves, as well as the logic solver will be required to have a fault-tolerant architecture. So in this case, here's a simplex architecture with 1 transmitter, 1 final element, and a single-channel PLC architecture. And this would be a fault-tolerant architecture where we have multiple field devices, both in terms of sensors and final elements, each capable of putting the process into a safe state, and a fault-tolerant CPU architecture. This would be a 1 out of 2 architecture to achieve a higher, perhaps SIL 2 or even SIL 3 level of compliance. A simplex or single device architecture is typically good for only SIL 1. More higher SIL levels would typically require more frequent functional testing, which is in an increased level of testing or decreased interval on the testing to ensure that if there are dangerous failures of components, that they will be detected during a described functional test and not be uncovered during a dangerous or demand condition. So for a SIL 1 requirement, we may have, say, turnaround testing intervals of every 2, 3, or 4 years, depending on the type of architecture that we've selected. For SIL 2 or SIL 3 requirements, this would yield typically more frequent functional testing requirements of, say, annually for SIL 2, and in the case of SIL 3, depending on the architecture that's been selected, may require something as often as quarterly functional testing. Diagnostics are similar to function testing, but are different in the respect that they perform their intended action typically during process operation rather than full function testing, which is an offline test procedure. Diagnostic testing can be either built in to a device, such as the overrange or underrange detection on a transmitter, or it could be bolt-on diagnostics, or diagnostics that we've configured as part of the system implementation, such as partial stroke testing or fault-tolerant solenoid-operated valve testing that allows us to, with some defined frequency, test the system automatically while online without providing any disruption to normal process operations. We use certain reliability models to combine these different factors, including the failure rates of specific devices, the fault-tolerant architectures, the functional testing, and the diagnostic testing. And those reliability models allow us to predict the achieved SIL, the achieved risk reduction, and even the spurious trip prediction, the frequency of a spurious trip for each of those safety functions on our SIF list. Those reliability models that are permitted within the standard include simplified equations, fault tree analysis, and Markov models, which have individual strengths and limitations, but all are considered suitable for determining the suitability of a particular design to be used in a SIL application. And that would be the SIL verification step. If we're unable to achieve our SIL target with a particular design as determined by these reliability models in SIL verification, then we would modify the design and correct it accordingly to achieve a higher level of SIL and an acceptable nuisance trip rate. The next step in the safety life cycle would be generating safety requirement specifications. There are a number of detailed specifications that are required per the S84 standard. Those generally can be described into specifications that describe the SIS behavior, how it should behave from a functional standpoint, the integrity specifications, including what it needs to do when certain fault conditions occur, and describing that in terms of a logic solver functional specification, which could be a narrative, could be a cause and effect logic diagram, it could be binary logic diagrams, as well as a series of general notes that meet all the specific SRS requirements of the standard to describe the behavior of the system when responding to fault conditions, to describe how often it needs to be tested, to describe the failure modes and the effects of those failures on the system. Usually, the next step is conducted by separate individuals, that there would be a certain demarcation between the conceptual design and the detailed design, and the interface between those two groups of people is the SRS. So the conceptual design is now finished, the detailed design needs to proceed, and it is done based on the requirements in the safety requirement specification. At this point in time, things tend to look more similar. Even though this is a safety automation project, the tasks tend to look more similar to any other instrumentation and control project. The most important step at this point in time is to ensure that the implementation is done precisely as per the safety requirement specification, which, if done properly, then should have codified all the requirements for the detailed designers in terms of how to meet those SIL targets that have been selected. So in detailed design, we're doing things like loop sheets, cable schedules, wiring diagrams. The PLC is being programmed and configured to achieve the functionality that's been described in the safety requirements specification, and the output of this step would be a detailed system design. Procedures include operating procedures as well as maintenance and testing procedures, and any procedures that would be required for an operating company to respond to fault conditions. In this case, procedure developments that are the most important are the functional testing procedures, those procedures that we're going to use to commission the system with, as well as the ongoing testing procedures which we'll use to regularly ensure that all the devices from the inputs through the logic solver to the final control elements are all operating properly to ensure that no fault conditions are there in the system. And there are test procedure templates that we use to ensure that each type of equipment is properly tested and thoroughly tested, such that the assumptions that were used when we did those reliability models for how frequently and how effectively things are being tested, those assumptions are being borne out in practice with a robust design, in this case, functional testing protocol. Next step in the safety life cycle is the construction, installation, and commissioning. This is where the system is brought to the site. Field wiring is installed, the SIS program is loaded, and the system is being commissioned at this point in time. We're going through it during that commissioning. We're going to do a very important step where we go through pre-startup acceptance testing to verify that all the equipment is installed in a way that conforms with the safety requirement specifications. We'll do a detailed assessment of the hardware and the software versus the safety requirements spec at this point in time, as well as doing a full range of functional tests on all the installed field devices through the logic solver to ensure the functionality is correct. Importantly, this is a step that's critical to do as the system has been fully commissioned at the site. There may be other types of testing that have been conducted up to this point, including a battery of factory acceptance testing, which is useful in determining there are no problems with the SIS programming and configuration, but pre-startup acceptance testing is the point at which all the field devices have been integrated and we have the opportunity to conduct a full assessment of the system before handing it over to the operations group. At this point, any deviations from the expected behavior of the system can be recorded on a punch list for correction before the system is started up. Operations and maintenance is the next and hopefully the longest duration step in the safety life cycle when periodic function testing is occurring. If there are any overt fault conditions, they will be responded to, and hopefully long periods of time where the SIS is performing adequately in a manner that doesn't disrupt process operations and, if necessary, is properly responding to demand conditions to shut the process down where necessary. Throughout operations and maintenance, there will be opportunities to assess and manage potential changes to the system. Most companies do have robust change management systems that are required under OSHA process safety management, and any changes that are being proposed to the safety instrumented system, changes that are non-like in kind changes, would typically be required to follow those management change procedures to be assessed prior to implementing any changes to ensure that all functional safety aspects are being achieved and that we haven't compromised in any way our ability to achieve the desired level of integrity. The SILs that have been selected in the initial process design can still be achieved even in the face of changes being made to the system. So those are the major steps in the safety life cycle. We are frequently asked, well, okay, what if I decide to implement this in my plant or process, what's going to be the impact? There will be a significant amount of analysis that is required, and certainly some, although not all new equipment, will likely be needed to cover situations where the existing facility is not, the existing systems are not adequate to achieve the SILs that are required of them, or situations where new safety functions need to be added. There will be some assessment and requirements in terms of maintenance and testing to ensure that those safety systems can meet the safety integrity level targets that have been specified, and often it results in an increase in level of effort, but some cases it actually might result in a decrease in level of effort where systems are heretofore being tested at an arbitrarily frequent basis rather than a basis that has a good or frequency that's got a good basis in terms of the safety of the system being achieved to a desired level of safety integrity. So those are some of the impacts that might typically be required in an implementation activity where a site has decided to implement ISA 84 for the first time. In terms of the key takeaway of this overall presentation, SISs are used in plants to reduce risk, not in and of themselves, but through a combination of systems of administrative controls and other layers of protection that provide a sound basis for risk reduction. There are various regulations that govern the safety instrumented system design. Here in the U.S., those are the Process Safety Management Standards by OSHA and the equivalent standards by the U.S. EPA. There are maybe one or more local standards or other good practice standards such as the NFPA that come into bear for specific SIS applications such as fired equipment. Users of safety automation, those would be operating companies, should and must have a program for SIS design and implementation. Those standards are performance-based. They're not going to prescribe every element of how to make a decision in every case, but a robust program provides a good basis for determining where existing equipment may be suitable for reuse versus where new equipment may be required and how frequently that equipment needs to be tested, as well as the design of that new equipment. Wholesale replacements of SIS across an entire plant site are rarely the case, but occasionally they may require extensive redesign and upgrades of SIS to achieve the new standard requirements, although it's almost always the case where existing systems, or at least some existing systems, are suitable for continued use in process plants. Those are the key takeaways from the Safety Instrumented System Lifecycle Overview presentation. I do appreciate your attendance and wish everyone a pleasant afternoon.